David Smith here with yet one more flipped classroom math lesson. 3 tips before we start. First, remember that you can slow down or speed up the playback to suit your needs. Second, you can pause the video at any point to catch up with your notes or jot down questions. Third, you can turn on the captions and read my words on the screen. Let's do a quick review of the first part of Chapter 3, which is what we've been working through in the last week and a half. So let's take a look. The first thing we did was in lessons 3A and B, we looked at gradients. One of the first parts there was the gradient of any kind of a line that had 2 points, x1, y1, and x2, y2. If you have any 2 points like that, you can calculate the gradient or the slope between them using this formula. Now, as you notice from the word problems, gradients are rates of change. And so they might apply in situations where you would not normally think of graphing a line and finding the gradient. But nonetheless, there's a rate of change that can be calculated. And strictly speaking, that would be a gradient. So we did a bunch of different problems calculating gradients between points and things like that. But we finished up by taking a look at a couple special cases, parallel lines and perpendicular lines. First off, the notation. Parallel lines are indicated this way. This says line 1 is parallel to line 2, and perpendicular lines are indicated this way. Line 1 is perpendicular to line 2. So, now, I want you to fill in the blank. Parallel lines have blank gradient. Go ahead and pause the video, put that in there. Parallel lines have the same gradient. So if you know one line's gradient and you're told about another line that's parallel, you know that it has the same gradient. Now we had some problems that were set up that way. Second thing, perpendicular lines have gradients related by, pause the video and fill that in. Okay, let's see how you did. They're related by the negative reciprocal. And this sounds kind of fancy schmancy, but it's actually a really simple process. You just take the fraction, flip it, and change the sign. So I want to give you one example. If line 1 has a gradient of 4/5, what's the gradient of line 2 if they're perpendicular to each other? Okay, if you got -5/4, you're right. As we moved on, we explored 3 different forms for line equations. The first form is probably the one that you're most familiar with. That's gradient intercept. The second form was a very useful one called point intercept. That was how we got into some line equations. And then finally we had general or standard form for a line equation. So I want you to pause the video and write down the general forms for these 3 types of line equations. All right, let's see how you did. Here's gradient intercept form. That's how we write that. F of x equals mx plus b. We could also write just y equals mx plus b. This is function notation. We spent a while looking at functions so far this year. Second one is point gradient. So this one is if I tell you the y-intercept and the gradient, you can write that equation without doing any calculating. This one, if I tell you any point that the line passes through and the gradient, you can plug that in. Gradient goes here, and the x1, y1 of that line equation goes there. When we do that, we always go from this form either to gradient intercept or to the last form, general or standard form. So let's look at that. General form is this way. ax plus by plus c equals 0. And you'll notice that my letters are uppercase. That indicates that they have to be integers, all of them, no fractions. So sometimes when you're coming from one of these forms to this one, that's the trickiest part. What do you multiply by to get rid of all the fractions? Okay, here's one type problem you might see. Convert to standard form. Notice this equation here is in gradient intercept form. We need to convert it to standard form. So the first thing to do is get rid of your fractions. Can't have them. All the coefficients have to be integers. So the easiest way to do that is multiply both sides by 4, like so. And I'm going to get 4y equals 3x plus 28. So that's multiplying through by 4. Now I need to rearrange it so one side is 0. And if you remember that lesson, we prefer to have the x term positive. So I'm going to subtract the y term from the left-hand side here and get 3x minus 4y plus 28 equals 0. Okay? Now there was a little trick I shared with you. You can get the gradient right out of here. The gradient is minus a over b. Here's my a, here's my b. So the gradient is minus 3 over minus 4, which is 3/4. So this line has a gradient of 3/4. And oh, guess what? That's where we started from. So we know we did that right. Here's another type of problem you might get. I have a line with a gradient of minus 5/3, and it passes through the point 1, -2. Go ahead and pause the video, see if you can use the equation form that relates to this from the last board and find that line equation. And I'm going to say, let's find it in gradient intercept form. Okay, let's see how you did. So I used my point gradient form. So I put in my 1 here, that's the minus as part of the formula. So I put my 1 in there, and then I have a -2, so it's minus 2. And when I work my math down, I get y plus 2. I'm going to distribute my negative 5/3 here. So I have minus 5/3 x plus 5/3 because we've got two negatives. Then I'm going to bring my 2 over by subtracting 6/3. And I have y equals minus 5/3 x minus 1/3. Now, for extra practice, convert that to general form. Let's see how you did. I multiplied both sides by 3 to get rid of my thirds. So I ended up with 3y minus 5x minus 1. And then I wanted to keep my x positive, so I moved all these over. 5x plus 3y plus 1 equals 0. We also discussed the special case of horizontal and vertical lines. So let's take a quick look at that. A horizontal line has the equation of y equals some number. What this means is the line's horizontal, so y never changes. X can change all it wants. Y is always going to be some number. So y equals, you're looking at a horizontal line. Now a vertical line is really similar, except that it's x equals some number. So it's vertical. It means it's going to go through one point for x. Doesn't matter what y is. X is always going to equal that number. So let's go over here and take a look at two examples. Here's a line going through the point x equals minus 5. The line is vertical, so the equation of that line is x equals minus 5. Here's a horizontal line, y equals 3. It's passing through the point y equals 3 everywhere, so it's horizontal. Pause the video and tell me what the point of intersection is for these two lines. If you got minus 3, 5, you're right. If you don't get that, pause the video, take a look at it, make sure you see why that's the point of intersection. One last point. We can talk about the slope or the gradient of horizontal and vertical lines. So pause the video, dig deep, see if you can remember what these slopes are. A horizontal line has a 0 slope. There's no rise. It makes sense. This is intuitive. To have a slope, it would have to be going up or going down. No slope. So the slope is 0. Now a vertical line is a little different, and it's kind of weird. We say the slope is undefined. Because remember, slope is rise over run. Now, if you look at a vertical line like this one, x equals minus 5, there's no run. It's always minus 5. So when we do this fraction, we'd have whatever number on the top with a 0 on the bottom, and mathematics doesn't handle division by 0 very well. In fact, it runs away screaming. We call it undefined. So remember, vertical lines have an undefined slope. One of the things we did is use linear functions to model or match data. So here's an example where I'm just giving you x and y values, but some of these problems were buried in word problems where there was an extra layer required to understand how to use the data. In this case, I'm just giving you a data table where you know that 1 maps to 19.75, 2 to 26.5, and so on. So here is the prompt for this one. Find the equation of this line, and I say there by using algebra. I am aware that your graphing display calculator, you can just put this table in there and it will give you the equation of that line. But if you're doing a test question that says by using algebra and you can't show algebraic steps, you're not going to get points for that question. So let's take a look at that. Our first thing is to find the gradient. Without a gradient, we can't write a line equation. We've got a bunch of points and we know we have point gradient form. So we can use any one of these points plus this unknown gradient, and that'll help us write the equation of this line. So you can check, if you know this is a linear relationship, you can find the gradient between any two of these points. I tend to go for the biggest spread, so I'm going to pick it between x1, y1, and x2, y2. But truth be told, you could do any 2 points in this table and you get the same gradient. So go ahead, you could pick a different 2 points, calculate the gradient for this table, and then come back. Let's see how you did. Here's my plug-in for my 2 points, my x1, y1, my x2, y2. I just plugged them in there following the formula, crunched my numbers, got 27 over 4, which reduces down to a decimal of 6.75. Either one of these are okay for your equation. Now, pause the video and do the next step. Let's see how you did. Use point-slope formula. Remember, I have my slope, my gradient, and I have a whole raft of points I can use. Any one of these points will work just fine. So I did my plug-in. I used this one because the rest of these have decimals, and I figure I like to do things in my head, so 40 is something a whole lot easier to manage. So I used 440, so y minus y1, there's my 40, equals 6.75, which is my slope, times x minus x1, which is my 4. And then I just crunched my numbers, simplified on down, and I get y equals 6.75x plus 13. And that's the equation that governs this table. The last thing we did in this section of chapter 3 was we looked at quadratic functions and their transformations. So a quick review of a basic form for a quadratic function. This is called vertex form because it gives you the vertex. This is a times parentheses x minus h squared plus k. And the vertex is hk. So that's the turning point of the parabola. That's where it changes from increasing to decreasing or vice versa. That is either a local minimum or a local maximum. So that's our vertex. We also have a symmetry axis. So that's the axis across which the parabola can just reflect itself right onto itself. And I'll put a graph up in a minute. I want to talk about the transformations. So A is a pretty complicated letter. It does a lot of things for our parabola. What I'd like you to do is pause the video and jot those things down. All right, let's look at A. A handles the compression or the stretching. So compression is when the parabola gets pinched and makes it more narrow. Stretching is when it opens up and makes it more wide. So when A is between -1 and 1, it opens it up, it stretches it. When A is either bigger than 1 or less than -1, it pinches it down, compresses it, or makes it more narrow. So that's the first thing that A does. A also controls whether it opens up or down. So I've got my little graphs here. If A is positive, it opens up. If A is negative, it opens down. So A is one of the most important things that controls the shape of the parabola. So that's a transformation of the mother parabola. Now I want you to tell me what H does in this part here. What does H do? All right, if you said that H does a horizontal translation, you're right. If H is plus, it moves left in the negative direction. This is the tricky thing about the H. If H is minus, it moves to the right. So it just takes that turning point of the parabola and moves it left and right. Last one, K. What does K do? K is the vertical translation. So K moves the graph up or down. If K is positive, it moves it up. If K is negative, it moves it down. So this one makes sense. Now I missed one thing. I didn't talk about what transformation the positive and the negative are. What kind of transformation does that happen? Like if I put a negative value in for A, that makes a transformation. What is it? It's a reflection. So we're going to reflect that parabola down across whatever horizontal line we have there, whether it's the x-axis or another horizontal line. One last board. Graph this function, the mother parabolic function, f of x equals x squared, and then on the same axes, graph g of x equals -3 times x minus 1 squared plus 2. Now, I'm going to ask that you don't use your calculator for this. I want you to get used to how to use transformations to create this graph. This graph you should have memorized. You should just be able to pull out a sheet of paper and throw that one down. And then if you understand all of the transformations here, you should be able to throw that one down almost as easily. So pause the video, get out your paper, and go ahead and put both these graphs on the same coordinate plane. All right, let's see how you did. So here's my mother parabola, centered on the origin. There's my vertex. I go over 1, up 1 for my first point, and then over 2, up 4 for my second pair of points. I just did that. Actually, I went over 3, up 8 for the third one. So that gives us our mother parabola. This parabola is related to it, but just transformed. So in a gross sense, my vertex is going to move to 1, 2. So here's my new vertex, 1, 2. With a negative 3, it's going to open down, and the number is bigger than negative 1, so it's going to compress it. So you can see from my graph there that indeed has happened. Now I used the function to generate my points so I could label them on my graph and made sure that they corresponded with the way I drew it. Now that you've watched the video, jot down some notes or questions for our next class. You can also re-watch the portions of the video that you didn't understand so well the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.